Good days, everyone. My name is Teo Chen Kiet, and I'm the fourth-year student who is currently studying Mechanical Precision Engineering in Faculty Malaysia, Japan International Institute of Technology. And today I would like to introduce to you guys about my FYP title, which is Dynamic Calibration of Thermocouple, and also my supervisor, who is mentoring me on doing this final year project, and his name is Professor Dr. Yutaka Asako. What actually leads me to doing this research is that the main reason that I want to do this research is just that to determine the thermal coefficients of the thermocouple when the size of the thermocouple junction changes. And the research objective of mine actually got two. First one, which is determine the effect of thermal coefficient of the junction of thermocouple, and the second one is perform dynamic calibration of thermocouple as well as gain more understanding towards it. So, in this era where the temperature sensor are widely used in the industry and also manufacture factories, so on. So there are actually three temperature sensor that I'm going to introduce to you guys. First, which is the thermocouple. The second one is the resistant temperature detector (RTD), and the third one is thermistor. There are actually a lot of difference between among these three temperature sensor, but they got characteristic, one similar usage, which is used to measure the thermal characteristic of gases, liquid, and solid in many process industry, and are configured for both general and special purpose usage. Since the FYP project of mine is focused about dynamic calibration of thermocouple, so I will introduce about the basic working principle of the thermocouple. So from this figure right here, we can actually see that there are actually two dissimilar metal, which is metal A and metal B. And there are two junctions. One junction is a hot junction and the second one is a cold junction. The connection point where the metal A and metal B are welded is referring to the hot junction, is where the temperature sources will detect the temperature and measure it. And the cold junction is the reference junction that we're going to create the difference between the temperature and thus produce the potential difference. Calibration, based on the Cambridge Dictionary, is defined as the units of measurement marked on an instrument so that it can measure accurately, and the process of checking a measuring instrument to see if it is accurate or not, and that is calibration. And there are actually two types of calibration, which are static calibration and dynamic calibration. In simplified word, the physical inputs of the static calibration will not vary along the time constant. Meanwhile, the physical input of dynamic calibration will vary significantly along the time constant. The purpose of having these two calibration is to minimize the uncertainty by ensuring the accuracy of the data. Now we will be talking about how to do these experiments. It's about the methodology. This experiment will be running through by using the simulation, which is this experiment is actually simulation based experiment. And the way how I'm going to get the result is that by using the window prompt as the main application to run Fortran code in G95 compiler. And the second thing that is that I will be using the SM4 Green application to do the graph plotting, and also the plot 7 to read the temperature changes of the insulator sheet thermocouple. Right here, this is a result of the case 1, which is the exposed sheet thermocouple simulation. We can see obviously like here, this graph is there are two information in this graph included in this graph. One is the changes of heat coefficient based on diameter, and another is the changes on diameter based on the heat coefficient. So there are four symbols right here, where the first one is a sphere, the second one is a triangle, third one is a square, and the fourth one is the spade, where the circle is actually representing the heat coefficient equal to 10,000, and the triangle is heat coefficient equal to 1,000, square is equal to 100, and the spade equal to 10. And there are two colors for the each of the shade, which is white and black. The white color actually representing the diameter of the exposed sheet thermocouple junction to be 0.005 meter, and the black one is actually 0.01 diameter. So if let's say we apply the condition where take the diameter of the junction as constant variable, we only need to comparing the data within the heat coefficient where we need to compare it sphere, triangle, square, and a spade with with their colors. Okay, so right here we can see that when the heat coefficient increases, the time constant to fully transfer the heat throughout the thermocouple decreases. And if let's say we put it for case 2 where we take the coefficient as constant variable, so that means we only need to comparing the white color shade with the black color shade. So when the diameter of the junction of the thermocouple increases, the heat to fully transfer through the thermocouple increases as well. So this is the result that we can conclude by doing the case 1 exposed sheet thermocouple using this simulation. So we are now moving to the case 2 where this shows the result of the second case, insulated sheet thermocouple. So there are actually three figures of the graph shown right here, where the figure 1 representing the effect of changes in diameter. The second figure is the changes in thickness of the sheet, and the third one is changes in heat coefficient. There are three colors of the diameter shown in figure 1, which the black color represents at 0.0002 meter, and the green color represents at 0.002 meter, and the red color representing 0.02 meter. Based on the figure 1 that we see right there, we can conclude that if the diameter of the cylinder increases, time taken for the heat to be fully transferred throughout the thermocouple increases as well. So we move on to the figure 2. Right here, there are three types of data showing right here, where the black color represent the thickness of a sheet around 0.005 meter, and the blue color representing around 0.05 meter, and the red color about 0.5 meter. For figure 2, when the thickness of a sheet increases, the time taken for the heat to be fully transferred throughout the thermocouple decreases as well. And last, for the figure 3. Figure 3 shows that changes in heat coefficient. How does these changes would affect the temperature response or the time taken for the heat truly transfer throughout the thermocouple? There are four colors of line for the data showing in the heat coefficient, which is the black color, green color, and blue color, and also red color. So each of them are representing 10,000, 1,000, 100, and 10 respectively. By comparing the four data line right here, we can conclude that when the heat coefficient increases, the thermal response of the thermocouple would increases, which means the time taken for the heat to be fully transferred throughout the thermocouple decreases. Where this the relationship between the thermal response of the thermocouple and the time taken for the heat to be fully transferred throughout the thermocouple is actually on the other way. So that's all for my presentation, and thank you.